Hello, this is Sean McGowan, and this is my video submission for Lab 6, Digital to Analog Conversion and Servo Motors for ENME 351. Here's our circuit where we have our potentiometer inputting to the A3 pin, and the servo motor is receiving its signal from the PWM pin 3 on our Arduino. By rotating and changing the input from the potentiometer, we'll be able to rotate the servo accordingly. Here's our code to control our servo with the potentiometer. In our code, we have our potentiometer being read from pin A5, and that is then being mapped into a range of duty cycles which can be sent to our servo. These duty cycles are sent to the servo using an analog write function, which then moves the servo in a range from 0 to 180 degrees. Then the whole process is delayed 20,000 microseconds for the period. The movement of the servo's 180-degree range is controlled using the potentiometer shown here. I also included the serial monitor to show the duty cycle which is being outputted to the servo. Here are our calculations for our 3-bit R2R DAC. We find with the full scale range voltage of 5 volts, our least significant bit is 0.625 volts, shown at the top corner. We then determined our Vout value for all bit settings by applying Kirchhoff's current law to the DAC and finding the bit relationship to Vout. Here we have our R2R DAC set up in Circuit Lab. We're using these 3 switches to change the 3 bits D0, D1, and D2 from high to low. We will simulate here the first 3 bit settings from our table to show the correlation. So here all bits are 0. We have Vout as 0. Next we'll change D2 to high, simulate that. We get the 2.5 volts, and then we will change D1 to 1 and D2 back to 0, and we get the 1.25 from our table. Here we've physically built the R2R DAC from Circuit Lab. For our resistors, we use 10K and 20K ohms for R and 2R respectively. We're using the orange wire to move D0 from 0 to 5 volts, yellow is for D1, and green is for the bit D2. The white wire is reading our Vout, which is being used to display on our serial monitor. We have our Arduino code, which is used to read the Vout from our DAC. The serial print function is set up to convert the analog input to a float in the range of 0 to 5 volts. Going through the bit settings, we see the experimental values for Vout are very close to our theoretical values, all within a 1.44% margin of error. If we needed smaller step size in our Vout from our DAC, we would need more bits so that we could have a higher resolution. For our 3-bit DAC, our step size is 0.625 volts, but if we had a 4-bit DAC, our step size would be 0.3125 volts. Using this 3-bit DAC, the servo has 8 possible positions it can move to, compared to the potentiometer, which has approximately 180 different positions. While the potentiometer allows us a smaller step size, the DAC allows us to have a much more accurate step. If we want a smaller step size and angular position for the servo, all we would need to do is add more bits to our DAC, which just means more rows of 2R and R resistors and more switches. And lastly, here's the code that we used to move the servo with the DAC. The only changes we really made was we added a float variable called duty, which represents the duty cycle, which we mapped from the input of the pin, which was 0 to 1023, to a range of 67 to 251, which I found worked best and most accurately with this servo. That is it for this lab. I hope you enjoyed, and I will see you next week.